Hello, knowledge seekers. In this episode of 20-Minute Books, we venture into the fascinating world of chaos theory with Chaos, written by the acclaimed James Gleick, charting a course through the tumultuous scientific revolution that tore through the foundations of classical physics. Chaos reveals how the seemingly disorderly and unpredictable forces of nature, from the patterns of the weather to the rhythms of the animal kingdom, embody an underlying, mysterious order. This groundbreaking work unpacks the historical evolution of chaos theory and stands at the vanguard in exploring its profound implications. Author James Gleick, revered as a luminary in science writing, has carved a niche as an expert chronicler of physics and technology. Not just a historian and journalist, his writing is credited with influencing pop culture, as he is thought to have inspired the character of Ian Malcolm in the movie Jurassic Park. Gleick's repertoire includes international bestsellers, notably the biography Genius, The Life and Science of Richard Feynman, which garnered international praise. Chaos is the perfect gateway for curious individuals who yearn to peer into the enigmatic abyss that is our universe, for those with a passion for the evolution of modern science, and for anyone who wishes to grasp the beauty and complexity residing within the chaos that surrounds us. Engage with this narrative that stitches together a coherent picture of a world where the chaotic is not merely noise, but a cipher waiting to be decoded. Join us as we unravel the intricacies of chaos theory, and let's get ready to be enthralled by the harmony within the pandemonium of the cosmos. Chaos, Making a New Science. Introduction. Embark on a journey through the patterns of unpredictability. Imagine a universe that ticks like a precise cosmic clock, where every shuffle of a leaf and every murmur of the wind are dictated by clear, undeviating laws. For centuries, that's how scientists viewed our world, as a grand machine following a predictable script. Randomness, irregularity, they were thought to be mere noise, brief disruptions that would inevitably resolve back into their proper, orderly place. Yet, in the tapestry of the 1970s, a radical change was sparked. A vanguard of thinkers dared to confront the aberrations, the strange and unsystematic behaviors that older models of physics had sidesteamed. With the dawn of the computer age, they were empowered to uncover chaos not as an exception, but a fundamental aspect of nature. Hidden within the intricate dance of weather formation, the seemingly haphazard dripping of a tap, or even the patterns that sustain the beating of our hearts. Unveiling the beauty of chaos theory. These explorations uncovered a groundbreaking revelation, that beneath the apparent randomness of chaos, there lies a secret structure, an unexpected elegance that weaves itself into the fabric of existence. This newfound understanding unveiled a whole new arena of scientific inquiry, chaos theory, which challenged the foundations of classical physics and introduced a mesmerizing vision, a world where order and chaos are not adversaries, but intertwined partners in the cosmic ballet. What you're about to discover is akin to beholding a magical realm where everything you know is turned on its head. Here, a butterfly flapping its wings in Beijing can be the architect of a tempest in New York. The perimeter of Britain emerges as an enigma, boundless in its measure. And even mosquitoes can experience the disorienting woes of jet lag induced in a lab. This is not just a fable of science, it is a testament to the incredible order that underpins life's complexity. So, let us explore this curious domain where chaos whispers the secrets of the universe and teaches us to embrace the unpredictable rhythms that orchestrate our existence. Part 1. Edward Lorenz and the Unraveling of Weather's Unpredictable Nature Trust in the Predictability of the Weather Forecast. A question many of us might chuckle at, but back in the buoyant 1950s, the burgeoning capabilities of computer technology filled meteorologists with unwavering confidence. The dream was to harness this tech not only to anticipate the weather, but possibly to bend it to our will. Scientists acknowledged the enormity of the task. The complexity of weather forecasting was not lost on them. However, with robust enough data feeding the hungry minds of powerful computers, the belief was that the weather could be forecasted with reasonable accuracy, even months in advance. This zealous belief in precise predictability was about to be challenged by the insights of an insightful meteorologist. Let me share with you how Edward Lorenz earned his title as the intellectual patriarch of chaos theory, thanks to his surprising findings on the unpredictability of weather patterns. In the year 1960, Edward Lorenz embarked on an endeavor to simulate weather conditions using the latest computer technology at his disposal. His ambition was to track and understand the evolution of weather patterns over time. During this pursuit, Lorenz made a groundbreaking discovery, a finding that would ricochet through the halls of science and upend our understanding of the weather, all because of an astonishingly minuscule detail. Upon reinitiating a weather simulation from its midpoint, inputting data manually from a prior output, Lorenz witnessed the two graphs begin in harmony, but slowly start to deviate from each other. Over time, the disparity grew until they bore no resemblance. The culprit? Lorenz had entered the data to the third decimal point, 0.506, instead of the full precision of 0.506127 used by the computer. This infinitesimal variation had the power to send the simulation spiraling into a wholly different pattern. Lorenz stood before an unexpected truth that contradicted then-current scientific doctrine. Minor fluctuations could incite massive repercussions in large-scale systems. Out of this serendipitous mishap sprang the theory of the butterfly effect, elegantly illustrating how delicate the balance of our weather systems is. The flutter of a butterfly's wings in Beijing could inadvertently set in motion a chain reaction culminating in a storm over New York. These observations, pinned down as sensitive dependence on initial conditions, provided the foundational principle for the emergence of chaos theory. It was a revelation that showed the universe to be rich with unpredictable twirls and whirls, a profound departure from the steadfast certainty once ascribed to weather forecasting. Part 2. The intricate dance of simplicity and chaos. Ever been a victim of the domino effect, where missing a simple bus led to a cascade of frustrating events? It's a practical, albeit exasperating introduction to sensitive dependence on initial conditions, a concept at the heart of chaos theory. Edward Lorenz, ensnared by the capriciousness of weather, illuminated that regardless of laying down a carpet of sensors at every foot of the Earth's surface, the weeks ahead in the meteorological calendar would remain shrouded in mystery. Weather dances to the rhythm of an aperiodic tune, almost cyclical, yet uniquely defiant in its refusal to strictly repeat a beat. What's more captivating is Lorenz's illumination of the undercurrents of almost order amidst the whirlpool of chaos. This narrative fairy isn't about chaos, it's about the rich tapestry of complex patterns woven from the simplest threads. Simple non-linear systems can weave a rich tapestry of complexity. Lorenz's endeavors led him far beyond weather simulations to uncover other systems where chaos reigned supreme. Among his findings, the simplicity of a water wheel stood out. Picturize a water wheel spinning as water tips into its compartments. Lorenz observed that a subtle increase in water flow could disrupt the wheel's steady rhythm, slow its spin, or even reverse it. Should the water rush forth with enough vigor, the wheel's motion became erratic, a paradigm of chaos. Both our intricate weather systems and this humble water wheel belong to the realm of non-linear dynamical systems. To demystify, a non-linear equation is akin to a maverick. The output it delivers may bear no rational proportion to the inputs provided. A non-linear dynamical system, thus, is a universe where small shifts can set off transformative consequences. Now, envision a swing, both driven by consistent pushes and restrained by the tug of friction. Against the grain of intuition, such a swing, a damped and driven system, may never settle into a rhythm of equilibrium, its pendulous dance an unending quest for balance. As Lorentz charted the cosmos of his three simple nonlinear equations, a visual marvel unfolded, a mesmerizing three-dimensional figure painting the air with what resembled the wings of a butterfly. The paths traced by this butterfly were quasi-cyclical, ever-changing pathways, reminiscent of elements from our world, the unceasing flux of weather, the capricious turn of a water wheel, or the chaotic fluctuations of a child's swing. Thus, a revelation cascaded through scientific thought. Mere equations, deceptively simple, could conjure vast, complex wildernesses of chaos. A revolutionary testament, and predictably, one that stirred the currents of resistance from those anchored to the old scientific paradigms. Part 3. The 1970s, a decade of discovery for nonlinear dynamics. For scientists, the accustomed linear narrative of the universe, where cause and effect line up like unwavering soldiers, was proving to be a stubborn illusion. Into this kingdom of order-chaos theory erupted like a revolution, led by a band of young, intrepid researchers in the 1970s. They were challenging not only existing scientific thought, but tapping into the core of some of the most fundamental principles governing our reality. To many established thinkers, chaos theory was a wrench thrown into the precise gears of physics and mathematics, unsettling, disruptive, and downright erratic. Before this upheaval, the universe was predominantly perceived and deciphered through a linear lens. Consider Galileo, the paragon of motion studies, who observed pendulums and perceived a flawless symmetry in their timing, regardless of the amplitude of their swing. Yet this, too, was a mirage. In the 1970s, physicists and mathematicians began giving non-linear systems the scrutiny they deserved. Galileo's belief that the pendulum would faithfully keep its rhythm under any condition was misled. The reality is riddled with non-linear chaos, mired by friction and air resistance, converting the predictable swinging pendulum into a beacon of chaotic behavior. Chaos became an intriguing playground for thought, with pendulums among the favored toys for scientific exploration. An array of researchers approached the non-linear cosmos, bringing varying lenses and tools to decipher its codes. Enter Stephen Smale, a mathematician stationed at the prestigious UC Berkeley, an explorer who traversed the paths of chaos unbeknownst to Lorentz's prior conquests. Smale specialized in topology, a brand of mathematics concerned with shapes that endure deformation, like a pliable universe that twists and turns yet preserves its intrinsic properties. Smale's genius laid in utilizing his spatial intuition to grasp the chaotic dance of electronic circuits, specifically the Van der Pol oscillator. Drawing upon his topological intuition, he conjured an enduring image, a rectangle transfigured within a three-dimensional space into a horseshoe. This shape, repeatedly squashed and stretched, demonstrated the unpredictable trajectories born from even the most adjacent starting points. Much to Smale's astonishment, chaos didn't equate to instability. He unearthed a startling paradox. Non-linear systems, despite their seemingly erratic behavior, often display a strange fidelity to their own chaotic patterns, resilient to the tumult of external disruptions. The full circle moment came when Smale made acquaintance with Lorentz's meteorological forays into chaos. A decade may have separated their discoveries, but the bridge they built spanned these realms of chaos, inviting a new pedigree of specialists. These pioneers were not merely entranced by the chaos itself, but by the promise of complexity and richness that sprang from the deterministic simplicity of these systems. Part 4. The mysterious ebb and flow of animal populations. Nature's repertoire encompasses an array of complex phenomena, and within its folds, non-linear dynamical systems emerge as a unifying thread. Perhaps one of the most striking examples of such systems lies in the delicate dance of animal populations, an arena where the principles of chaos theory play a pivotal role. In the biological domain of ecology, which scrutinizes the patterns of life over time, the interplay between species and their environments is a living testament to the non-linear dynamic. Here, scientists track the rise and fall of populations, dissecting the rhythmic heartbeats of ecosystems. Animal populations tell a tale of non-linear dynamism. If you've ever watched with fascination as a small pond blossoms with fish or observed a forest humming with the incessant chatter of insects, you've witnessed the non-linear dynamics of animal populations at play. Initially, a burgeoning populace accelerates in growth, but as constraints such as limited food sources come into play, the equations governing their expansion become increasingly complex. Occasionally, the pattern crescendos into a sudden, dramatic decline, an event recognized as a boom and bust cycle. Ecologists often turn their gaze to specific populations, like the gypsy moth, to understand how they vary over time. In nature, these changes are fluid, a seamless transition from one number to the next. But the differential equations that capture this smooth, non-linear evolution are mathematically demanding and often shunned by biologists more invested in life than in numbers. As an alternative, difference equations offer a more digestible approach, providing snapshots of change at discrete intervals, say, annually. A fundamental equation that bounds the growth of populations like a leash, curbing their expansion, is known as the logistic differential equation. For many ecologists, it was a safe bet that this equation would eventually lead populations to a stable equilibrium. That is until Robert May, an ecologist, decided to tweak his theoretical animal populations to the extreme. Robert May's discovery of chaos in population growth. May's experiments revealed a curious phenomenon. Introducing an element of boom and bustiness into the model led to erratic behaviors. At first, the population's cycles would neatly double in time and then double again, creating a series of period doubling bifurcations. As this process unfolded, the population behavior derailed into chaos. Unraveling this mystery, May consulted his mathematician friend James York. In York's seminal work, Period 3 Implies Chaos, it was made clear, once a system begins to fragment into these period-doubling bifurcations, the descent into chaos is imminent. York posited that the scientific proclivity to sidestep such irregularities was due to a resistance to acknowledge the chaos simmering beneath the surface of their studies. Robert May, however, chose to openly embrace these chaotic underpinnings, extending his profound insights from ecological realms into the world of epidemic patterns. His was among the pioneering spirits to seriously consider bifurcations, embracing the chaos as an integral part of the natural order. Part 5. Benoit Mandelbrot, Unveiling the Hidden Patterns of Complexity. The mathematician Benoit Mandelbrot had an innate knack for venturing into realms that were less than welcoming. His journey began with a flight from Poland to France in the turbulence of the 1930s, followed by a stint at the École Polytechnique, where his distinct visual take on mathematics found little favor in the prevailing climate of pure math supremacy. Driven by his unique visions, Mandelbrot made his way to the vibrant intellectual stomping grounds of IBM's Research Center in New York. During his IBM tenure, Mandelbrot was drawn to the whirling patterns of economics. The behavior of cotton prices across the 19th century drew his gaze, providing a portal into what would become his most defining revelation, the endlessly repeating complexities that stitch our universe together. Mandelbrot's fractal geometry exposed the elaborate architecture of dynamical systems. Economists back then clung to the conventional wisdom that while short-term price movements jittered randomly like leaves in the wind, the long-term swings adhered to the gravity of substantial economic shifts. Yet, the historical dance of cotton prices defied this simplistic harmony, refusing to gravitate towards any clear average. Armed with the computing might that IBM offered, Mandelbrot delved deep, only to emerge with a striking insight. The day-to-day fluctuations and the monthly variations were uncannily reflective of one another, revealing patterns nested within patterns. This symmetry of scaling seized Mandelbrot's imagination, prompting the realization that this phenomenon extended beyond economics, echoing in the fractal silhouettes of nature, the mountains, the clouds, all mirroring their grandiosity on a diminutive scale. Thus rose the concept of self-similar or fractal structures, a harmony that transcended sizes and scales. Consider the riddle Mandelbrot presented. What is the length of Britain's coastline? At first glance, it seems a ruler and a map would suffice. But Mandelbrot prodded deeper, questioning whether all the intricate curves and crannies were accounted for. Walking every inch of the coast, tracing every rock, however small, suggested the closer one looked, the longer the coastline became. Zoom in further, down to the atomic scale, and suddenly the coast of Britain sprawled towards the infinite. It was in this dance between the tangible and the boundless that Mandelbrot's fractal geometry thrived, encapsulating the raw, untamed, and fragmented essence of our world. His geometric narrative, rife with elegance and beauty, quickly rocketed Mandelbrot to academic fame. The hauntingly intricate patterns that are the fractals grew to symbolize the visual essence of chaos theory, showcasing a universe ordered not in straight lines and circles, but in the wild, unpredictable yet infinitely precise language of fractals. Part 6. The Complexity of Turbulence and the Power of Strange Attractors. Among the greatest enigmas of physics, turbulence has long stood as a quizzical challenge, poised with the kind of complexity that would provoke the pondering mind of Werner Heisenberg. Indeed, as the celebrated physicist lay awaiting his final moments, he mused over the perplexities of relativity and the baffling nature of turbulence. The latter, a riddle so confounding that even a divine entity might find it a tough query to resolve. Turbulence is a phenomenon that permeates our world, characterized by the sudden transition from a smooth, orderly flow to a chaotic tumble of currents and vortices. It's a concept that fascinates and terrifies in equal measure. A curl of cigarette smoke can captivate the eye, while the choppy currents beneath an airplane wing can set hearts racing. For too long, the intricacies of fluid dynamics were a Gordian knot left for engineers to untangle, as physicists found little hope in making theoretical progress. However, the advent of chaos theory signified a possible breakthrough. Strange attractors became the key to decoding the enigma of turbulence. The traditional linchpin of our understanding of turbulence hinged on the thoughts of Lev Landau, the Russian physicist who contemplated the particles within a fluid, each influenced by its neighbor. As the flow escalates, so does the complexity, with particles gyrating with greater degrees of freedom, stirring the pot that is turbulence. In 1973, physicists Harry Swinney and Jerry Golub put Landau's gradualistic theory to the test using a meticulously constructed system showcasing the crescent dance of fluid between two cylinders. As the cylinder's rotation accelerated, the smooth waltz of the liquid distorted into chaotic flux, defying the expected gradualism. Instead, they found a disjointed blend of tranquility and turbulence coexisting within the flow. Along came Belgian physicist David Rouelle, armed with a presentation by Steve Smale and his own contemplations on an alternative theory of fluid dynamics. Rouelle introduced a novel idea, visualizing turbulence through plotting its trajectory in phase space, an ethereal realm where every conceivable state of a system finds its place. Within this space, some systems are drawn to attractors, be they fixed points of equilibrium or repeating cyclical behaviors. Rouelle uncovered a breed of attractors, which he termed strange attractors, characterized by an orbit about certain regions in phase space, never exactly repeating their path. These strange attractors, when applied to physics, unlocked a new perspective on the unpredictable nature of turbulent flows. As scientists warmed to these ideas, they began to discover these strange attractors within the chaotic wonders of the natural world. astronomer Mikkel Hennon noticed that star orbits in globular clusters reflected the patterns of strange attractors too. Notably, Edward Lorenz had voyaged into this uncharted territory much earlier. When he mapped his pioneering nonlinear system, what emerged was the double spirals of the Lorenz attractor, the first strange attractor ever described, strikingly similar to the double spirals he had identified when unraveling the turbulent motions of the atmosphere. Lorenz's attractor serves as a testament to the intricate beauty hidden within the maelstrom of chaotic systems. Part 7. Mitchell-Feigenbaum's Breakthrough in the Universe of Chaos. The nocturnal meanderings of a maverick mind amid the hushed halls of the Los Alamos National Laboratory in 1974 might have raised security eyebrows, but they were merely the external ripples of an intellectual storm. Mitchell-Feigenbaum, the disheveled genius in their midst, was caught in the throes of a revelation that would etch his name into the chronicles of chaos theory. Feigenbaum, whose brilliance was acknowledged with a mix of awe and mystique by his peers, was charting his course through the wilderness of chaos by examining rudimentary non-linear equations, akin to those that fascinated ecologist Robert May in his studies of animal populations. He was drawn to the enigma that simplicity could be the mother of complexity, and that equilibrium was a stranger to some systems. Feigenbaum's journey led him to decipher universal truths hidden within nonlinear systems. Feigenbaum was particularly captivated by a type of nonlinear system known as almost intransitive systems. They could comfortably meander around one average state, only to jarringly swap to a different one without warning. An intriguing scenario that mirrored the hypothesized white Earth, an Earth so shrouded in ice that it would repel the sun's warmth, spiraling into a frigid alternative climate. The question begged to be asked: why hadn't Earth experienced this drastic state change over the course of its history? This boundary between calm and chaos, where transformation into a new average state becomes inevitable, became Feigenbaum's obsession. With calculator in hand, he delved into the period-doubling bifurcations of nonlinear equations, seeking the precise point at which order succumbed to turbulence. A pattern began to emerge, a geometrical convergence that Feigenbaum discerned in the numbers. Astoundingly, he gleaned the ratio of convergence, 4.6692016090, an esoteric figure that, when put to the test, proved resoundingly constant across different nonlinear systems. Feigenbaum, in his laboratory seclusion, embarked on a relentless pursuit of his new theorem. Laboring intensely, he distilled the essence of the Feigenbaum constants, an epiphany that would resonate through the corridors of uncertainty. The discovery of the Feigenbaum constants signified a turning point, introducing the concept of universality to the study of chaos. Where chaos had once seemed an ocean of endless variety, Feigenbaum revealed that even within its roiling depths, some aspects were predictable, steady beacons in the unpredictable tide. Although a mathematical proof would only surface in 1979, the introduction of the Feigenbaum constant served as a unifying force, invigorating the field of chaos theory with newfound stature and credibility in the skeptical eyes of traditional scientists. With Feigenbaum's findings, chaos theory was no longer a fringe curiosity, but a profound inquiry into the heartbeat of the universe. Part 8. The Santa Cruz Vanguard and the Democratization of Chaos Theory. In the late 70s, the embryonic rumblings of chaos theory resonated through the scientific world, stirring up an intellectual ferment among the academic community. By 1977, with the winds of change blowing, chaos theory was no longer just a whisper on the lips of the avant-garde. It took center stage at a major conference in Como, Italy. Yet, for the eager young scholars yearning to delve into this brave new world, guidance was sparse. The academic landscape had yet to catch up with the chaos unfolding. Enter Santa Cruz, where at the University of California's burgeoning campus, a cadre of maverick mathematicians decided to blaze their own trail. It began with Robert Shaw, a reticent graduate student enchanted by the fractal finesse of the Lorentz attractor. Stumbling upon the vast analog computer that graced the campus, Shaw began his solitary dance with chaos, tweaking knobs to visualize Lorentz's sensitive dependence on initial conditions. Shaw's solitary pursuit soon became a collective fascination. Before long, Doyne Farmer, Norman Packard, and James P. Crutchfield, who brought a flair for computers, rallied to his side. Together they formed the Dynamical Systems Collective, a moniker that, to some, rang as the Chaos Cabal. This young collective embraced computer visuals and common curiosities to bring chaos theory to the masses. The ferment of creativity in their haven of high-tech gadgetry was palpable. Amid plotters, converters, and myriad devices, they conjured visuals of chaos, pinning down patterns within the apparent randomness. Their forays ranged from pondering the tales told by the shape of a strange attractor to forging ties with information theory, renowned for its focus on the coding and relay of digital knowledge. A cornerstone of information theory, entropy, that inexorable slide towards disorder, piqued the collective's interest. According to them, strange attractors were the maestros orchestrating this entropic symphony, ushering systems into states of heightened pandemonium. Their work, however, transcended the exclusivity of academia. They painted chaos theory with a quotidian brush, probing the chaotic nature of routine occurrences. In the relaxed atmosphere of local cafes, they'd muse over the whereabouts of the nearest strange attractor. Is the vibrato of a car fender subject to chaos? Does a flag caught in a gust exemplify nonlinear phenomena? Shaw even turned his attention to the rhythm of a leaky faucet, unveiling the unexpected complexity lurking in its drips. It was this blend of the everyday with cutting-edge computer visualization that shot chaos theory into the limelight, sparking interest across diverse fields from economics to ecology. The Santa Cruz visionaries didn't just dip their own toes into the waters of chaos. They beckoned an entire generation of scientists to dive into the swirling currents of this revolutionary perspective. Part 9. The omnipresence of nonlinear systems in nature and their role in our biology. As the chaotic undercurrent of the universe gained recognition among the scientific community, the prevalence of nonlinear dynamical systems became increasingly apparent, unearthing their ubiquitous presence in the natural world. In a striking example, French physician Albert Liebschaber endeavored to put the concept of chaos observed in fluid dynamics to the test. His meticulously crafted experiment, featuring a tiny vessel filled with liquid helium sandwiched between two heated metal plates, became a microcosm for chaos. As the temperature difference escalated, so too did the complexity of the helium's movement, unfolding a dance of period-doubling bifurcations, much to the predictions of Feigenbaum. Liebschaber postulated a compelling hypothesis. Nature leverages nonlinearity as a shield against the unpredictable, a way to recalibrate after disturbances. Unlike a linear system that could be forever derailed by the slightest push, nonlinear systems possess the remarkable resilience to veer back to a semblance of normalcy. Nonlinear dynamical systems are a thread, interwoven into the fabric of nature, vital to understanding our own biology. The 1980s bore witness to physicians corroborating Liebschaber's insights, linking chaos with the workings of our bodily functions. At a pivotal medical conference, physicist Bernardo Huberman unveiled a nonlinear model describing the erratic eye movements traced by individuals with schizophrenia, as they struggled to follow a simple pendulum. The presentation was a revelation, marrying the universal laws governing motion with the biological rhythms intrinsic to the human body. Our hearts themselves are paragons of oscillation, with even minor aberrations in rhythm signaling potential peril. The chaotic disarray known as ventricular fibrillation, where the harmony of a heartbeat is disrupted, causing heart muscles to flail out of sync, stands as a testament to the heart's inherent nonlinear dynamic nature. These heart rhythm disturbances have yielded tragic, sudden deaths, forcing physicians to acknowledge the heart as a system susceptible to tipping into chaos with a miscalculated impulse. However, in the hands of modern medicine, chaos theory also provides hope. The defibrillator, delivering a calculated electrical jolt, operates under the same principle, harnessing a controlled shock to reset the heart's erratic dance and restore its steady beat. Beyond the heart, the lens of chaos theory has widened to include an array of dynamical diseases, ranging from respiratory disorders to specific forms of cancer and possibly even the elusive schizophrenia. Einstein once staunchly declared that God does not play dice with the universe. Yet the explorations spawned by chaos theory prompted physicist Joseph Ford to offer a playful counter. Yes, God does play dice, but these are not ordinary dice. They are loaded dice. The grand pursuit that lays before us is to decipher the rules according to which they are loaded, an endeavor that continues to fuel the restless curiosity propelling modern physics forward. Final summary. Our journey through the enigmatic world of chaos begins with a meteorologist named Edward Lorenz, who, in the 1960s, stumbles upon a bewildering phenomenon during weather simulation. His discovery opens the doors to the realization that the universe is filled with systems where seemingly simple rules can give rise to extraordinarily complex, unpredictable behaviors. The crux of nonlinear dynamical systems, the revelation that our reality is replete with such chaos, pervasive in the atmosphere, the intricate patterns of animal populations, and even the mechanisms of our heart, marks a seismic shift in scientific perspective. But within this realm of unpredictability lies a hidden layer of intricate order. Enter the world of mathematician Benoit Mandelbrot, who delves into the concept of fractals, unearthing self-similar patterns that reflect a startlingly ordered chaos across scales. Then there is Mitchell Feigenbaum, whose discovery of constants within the chaotic fluctuations of nonlinear systems points to universal laws underpinning the tangled complexities of nature. These trailblazers, amongst others, showcase that the chaos surrounding us, while seemingly capricious and ungoverned, is underlined by an elegant and profound order, echoing through the chaos of our world and resonating with strange beauty. Thank you for joining me today on this journey of learning and discovery as we explored the insights of another thought-provoking book in our growing library of knowledge. If you've enjoyed our time together, please take a moment to follow our podcast, give us a 5-star rating, and share 20-minute books with other knowledge seekers. Your support truly means a lot. Don't forget to join me again in the next episode, where we will delve into another enriching book. Until then, happy reading and happy listening.